Welcome to a presentation by Exact Education. The purpose of this video is to explain how to analyze an AC circuit using complex numbers and verify your calculations via an online simulator such as Multisim. This is a parallel circuit. There's three loads, there's three branches in the circuit. The first branch is resistor R1 on its own. The second branch is a resistor plus an inductor to mimic an electric motor. And the third branch is a capacitor to mimic power factor correction, adding a capacitor across a motor to pull the lagging current back as close to in phase with the voltage as possible. Signal generator 30 volts, 1000 hertz sine wave. Bit of background information. A resistor does not store energy. It does work. It converts electrical energy to heat. Capacitor stores energy, does not do work, stores energy in the electric field between the plates. Current leads the voltage in a capacitor. In an inductor, does not do work, it stores energy in the magnetic field. Current lags the voltage in an inductor. In our circuit, we have a combination of resistors, inductor, capacitor. If we want to calculate currents in each of those branches so that we can add those currents together to calculate the supply current, Ohm's law still applies, Kirchhoff's law still applies, whether you've got an AC circuit or a DC circuit. In this case, we want to add up the three branch currents to give us the supply current. This summation is in two dimensions. It has to be in size and angle because we have energy storage elements in the inductor and the capacitor. In order to calculate the current through the first branch, Ohm's law, voltage divided by resistance. In the second branch, voltage divided by impedance. The impedance is in two dimensions. Third branch, voltage divided by impedance again, and we'll do these detailed calculations in the next slides. Just a reminder, in Cartesian form of a complex number, the J operator is indicating a rotation of 90 degrees. That facilitates, we've got a horizontal dimension given by the value of R2 in this second branch, and we have a vertical dimension indicated by the number associated with the J operator. First branch, Ohm's law, voltage 30 divided by opposition to current flow 5 in the resistor, we have 6 amps. There is no energy storage in a resistor, so 6 amps at an angle of 0 degrees. So if we want to write out fully in complex numbers, Cartesian form, 6 plus 0J. Second branch is more involved. We have Ohm's law again, voltage divided by impedance. Our impedance is in two dimensions. We cannot directly solve a division in two with complex numbers. So what we do is we use the trick of complex conjugate to multiply the top and the bottom of our fraction here, the numerator and denominator, by complex conjugate of the denominator. In this case, we're multiplying top and bottom by 2 minus 6j. If we multiply both the top and the bottom of our fraction by the same number, we are not changing the fraction. And the reason why we're doing that is what we want to end up with is a real number with no imaginary components so that we can divide out and get an answer at the end. So in order to get there, top and bottom by 2 minus 6j, we'll leave the top part just now. We'll do the more involved multiplication of two sets of brackets here, 2 plus 6j times 2 minus 6j. If we multiply out the brackets, we have 4 products here. We have 2 times 2, we have 2 times minus 6j. We have 6j times 2. We have plus 6j times minus 6j. We have 4 products added together. So we end up with 2 times 2 is 4. We end up with minus 2 6j. We end up with plus 2 6j. Those numbers cancel out. We end up with 6 times 6 is 36, minus 36j times j, but j squared is minus 1. So we end up with 4 plus 36, which gives us a real number, no imaginary parts on the denominator, and comes out to be 40. If we then turn our attention to the numerator, we have 30 times 2, 30 times 6j, and again we have to divide each element by 40 from the denominator. So that gives us 60 divided by 40, 1.5, 180 divided by 40 minus 4.5j. This number indicates that we have a lagging current. The current lags in an inductor because of the magnetic field. We now turn our attention to the capacitor branch. Again, voltage divided by impedance. Impedance of the capacitor is minus 9j. So we multiply top and bottom by plus 9j. If we do that to the denominator, the j squared is minus 1. We have minus j times plus j, so it's minus minus 1. 9 times 9 is 81. So we end up with plus 81 in the denominator. Again, real number, no imaginary parts. On the numerator, we have 9 times 30 gives us 270j, divided by 81 gives us 3.33j. The j operator indicates there's no horizontal dimension here. The current in a capacitor leads the voltage by 90 degrees. What we can now do is take each current defined as a Cartesian form, a complex number. We can add the horizontal dimensions together. We can add the vertical dimensions together. If we draw a rough and ready phasor diagram, we've got an in-phase current for the resistor, an out-of-phase current for the branch 2 for the motor, and then we have a 90 degrees for the capacitor current. If we add all 3 vectors together, we get a final vector, which is the supply current. If we do it in terms of numbers, add the currents together in 2 dimensions, Cartesian form. In the horizontal direction, we've got 6 plus 1.5. In the vertical direction, we've got minus 4.5 plus 3.33. So we end up with a Cartesian number of 7.75 minus 1.17j. If we convert our Cartesian to polar form of size and angle using trigonometry, we have a right angle triangle. We want to know the length of the longest side. That gives us the size of the supply current. If we do the calculations using Pythagoras, we've got 7.5 squared plus 1.17 squared, and then take the square root of the sum. We end up, for the supply current, the size of it is predicted to be 7.59 amps, and its phase shift with respect to the voltage across it would be 8.9 degrees lagging. The lagging is indicated by the minus number in front here. So if we want to validate these numbers to see if our calculation is correct, we can put that circuit into Multisim, and we're looking for 7.59 amps is a measurement from a meter and a phase shift of 8.9 degrees. So if we then put that circuit into Multisim, we can work it out. Just before we show that, the reason why our capacitor has got a value of 17.68 microfarads, well, that value comes about because we want the capacitor to have an opposition to current flow of 9 ohms. That was how we started off in Cartesian form with the circuit at the beginning. So if we use the impedance of a capacitor as 1 divided by 2 pi fc, We don't know what the capacitance values is just yet when we start off, but we do know its opposition to current flow, which is 9 ohms. If we transpose equations and jump through the number crunching as shown on the slide, we get a value of 17.68 microfarads at 1000 hertz will give us an opposition to current flow of 9 ohms for the capacitor. In a similar way, we have an inductor that's got an opposition to current flow of 6 ohms. XL is equal to 2 pi FL. If we transpose these equations and put in the numbers 1000 for the frequency F, we work out that our inductor, to give us an opposition to current flow of 6 ohms at 1000 hertz, would be 955 microhenries. If we put those values of components into our multisim, put the circuit in parallel form, 30 volts peak, 1000 hertz sine wave going in. We have our ground reference in here. We have branch 1, R1. We have branch 2, resistor and inductor to mimic a motor. And we have power factor correction with this capacitor here. If we put it through the simulator, what we can see here is the solid green is the voltage going in. The dotted blue is the supply current coming out. What we can see here is this smaller sine wave here is the capacitor current, capacitor branch. You can see at the very start when the voltage is 0, the capacitor is at a maximum value. So the capacitor current leads the voltage by 90 degrees. The supply current is the dotted blue line here, with cursors put onto the peak of the supply current. We get a value down here of 7.61, which matches up very closely to our calculation of 7.59. Why would there be a slight discrepancy of 0.02? Well, 2 reasons. One is the eyesight as to where you exactly put the cursor on top of the waveform, and also the number of decimal points we're using in our calculation. If we want to look at the phase shift, what we can see here is the voltage crosses the 0 axis at time 0 here, and a little bit later the supply current crosses the 0 axis at this point here. There's a very small time difference, which is phase difference here, which is 90 degrees here, 180 degrees here. It's a very small phase angle. It's below 45 degrees. You're talking 10, 15 degrees here, just looking at it by eye. We can see that the supply current lags the voltage by a very small phase angle. If we want to measure this accurately, we can zoom in the horizontal, which has been done on this slide. If we put a cursor on the voltage here, and we put a cursor here on where the current, supply current crosses the 0 axis, we can see here that we have a time difference of 24.173 microseconds. Now, what we want to do is translate that into a phase angle. We have 1000 hertz sine wave going in, which is 1 millisecond time period, which is 1000 microseconds. If we want to translate this time difference into a phase angle, we can do the maths. We have 24.173 as a fraction of 1 cycle, which is 1 millisecond, because it's 1000 hertz signal going in. That gives us a fraction of 0.024173. If we multiply by 360 degrees, we come out to an answer of 8.7 degrees, and that is lagging as shown by looking at the waveforms coming out. So what we have is a phase angle calculation of 8.9. In the simulator, using our eyesight and the cursors, it comes out to be 8.7. So those values do verify our calculations within reason. There is very little difference between them. That can be taken into account by decimal point rounding off, and also by the accuracy or the resolution of the simulator and how good your eyesight is. Thank you for watching, and I hope that has been helpful in terms of being able to analyze an AC circuit. Thank you.